Wednesday night if it's clear and come along and do the observing. But meanwhile, we've got Mr. Ed and he can talk to you. We're going to start off with Chris in a minute. But after that, there'll be a tea break and juice and biscuits. And then those who want to stay are welcome to come in and hear, is it one or two more talks? Two? Right, charades, 2 talks. First one, I can tell you, is called When Gravity Takes Over. And talk number 2 is... It's the same. If you want everything to be made clear, come back after tea. The other thing I need to remind you, if anybody's interested in grabbing the Science Festival programme, I do have a stack out by the postcard table and by the tea table. If you want one, I don't have enough for everyone, so first come, first serve. But the online programme is, I've given the web address and the handout today as well. There are a few seats down at the front if you. Anyway, this evening, Chris, who's one of our research students here at the Institute of Astronomy, is going to be telling you how to build a rocket. So, thank you, Chris.
Hi everyone, can you all hear me at the back? Yes. Right, so today I'm going to talk about how to build a rocket. Now, I think rockets are really cool. That's why I wanted to give a talk about it. As Caroline said, I'm a research student. I live over in the Cavalry building. I don't actually live there, but it seems like it sometimes. So I've been here for 2 years now. I'm here for another year and a half, so I thought it was about time I gave these talks. So why do I think rockets are cool? Well, they're some of the most powerful machines humans ever built. If you've ever used a GPS unit, satellite phones, Sky TV, these have all been made possible by the use of rockets. So what am I going to talk about tonight? Well, I'll start off with a history of rockets. Since the dawn of the modern era, man has wanted to fly, and I'll try and take you through how we've tried and failed in the past and how it's come to where we are today. And then about the different types of rockets. There's hundreds of different types of rockets from different countries, different designs. Then I'll try and explain how they work, and then finally I'll talk about why we use them in astronomy and how the experiment that I work on used a rocket to get to where it is at the moment, which is about 1 million miles away from the Earth. So if we go back to 600 BC, the ancient Greeks longed to fly. They're gods, most of them could fly. There was the famous story of Icarus who wanted to fly and attached feathers and wax to his skin to try and fly, and unfortunately he got a bit too close to the sun, the wax melted and he fell into the sea. Fast forward another 1,000 years, there's a story of a Chinese general called Hu Shu who wanted to get to the moon. So here's Wu Shu. He attached 100 rockets to his chair. These were just simple tubes filled with gunpowder. He attached them to his chair. He had 100 assistants, all with lit matches, running forward to light the rockets. They ran forward, lit the rockets. There was a big bang and a puff of smoke, and Hu Shu disappeared. Maybe to the moon, maybe not. Wind forward another 1,000 years. The first designs for what we would now consider as a modern-day rocket were created by some Polish chap. I'm afraid I can't quite pronounce his name. I think it's Siemianowicz. And this is the first time that there's historic documented evidence of what we would now think of as a modern rocket. It was a multi-stage rocket, so it had different parts that ignited at different times to create a more sustained fire when he launched it. He didn't actually build it, it was just designed. So wind forward a little bit further, so 1800s, rockets were, the design was improved slightly, so they were made out of wooden tubes filled with gunpowder, and they had a long wooden rod to try and aim them at enemy ships. And the idea was they would try and land on the ships and set fire to the enemy ships. But they weren't just used for warfare. So in 1850, they were used on many occasions to save stranded sailors at sea. So a long piece of rope was attached to the back of the rocket. The rocket was fired to the ship, and there was a line on which the sailors could use to get back to shore. And this saved over 1,000 lives using this method. It was only in the 1900s that people started looking at rockets as a scientific experiment. So seeing what kind of properties these could have if you used different kinds of fuel, how high could you launch them, what were the different properties if you used metal or wood. And then in about the 1950s, we have the advent of what we now think of as a modern rocket. So the first ever Russian satellite was called Sputnik. Here's a picture of Sputnik. It's not very big. And here's part of the original design team that helped to design it. It was launched on one of the Russian rockets. It was in orbit around the Earth for a couple of weeks, sending back a characteristic beep, beep, beep signal, which contained information about where it was, how high it was, and what the outside temperature was. And this was the first time that anybody had launched a satellite into orbit. So obviously this annoyed the Americans. Not to be outdone, a year later, they launched their first satellite called Explorer-1, of course heavily publicized, so the Russians would get annoyed, and this ignited the space race, which ultimately led to man being put on the moon. So here's Explorer-1, not much bigger than Sputnik, but it contained a few more instruments, things like they could measure tiny meteor hits, so if the rocket was hit by a tiny piece of stone, it would send that data back to the Earth. And this was in orbit for a couple of months, so the batteries lasted on it a lot longer, and it was a much better design than Sputnik. And then only 10 years later, Apollo 11 puts man on the moon. So at the time, Apollo 11, all of the Apollo missions were launched on a Saturn V rocket, which was the largest, most powerful, and the heaviest rocket still has ever been designed today. Even the modern space shuttle is not as large as the Saturn V rocket. So that's a bit about the history of the rockets. How do they actually work? Well, the principle stems from Newton's third law, which means every force has an equal and opposite force, or reaction. Every reaction has an equal and opposite reaction. So I'm sure you've all seen this effect. If you fizz up a bottle of Coke, you bring the air and the liquid out of the liquid and into the space at the top of the bottle. The air compresses and the pressure increases, and then if you open the top, all of the Coke or the air comes fizzing out the bottom. So if you shake it up, the pressure builds inside, and then when you open the nozzle, the bottle takes off. So exactly the same principle applies to modern rockets and the space shuttle, but they don't use air as fuel because that wouldn't get you very far. When you open the top of a Coke bottle and fizzes around a bit on the floor, it's not going to get you to the moon. So rockets use a mixture of chemicals as their fuel instead of air because these give much more energy when you combine them together. So there are two main kinds of rockets used today, solid rockets and liquid rockets. And as the name implies, the only difference is the fuel is either in a solid or a liquid state. And these have several differences, which is why they're used for different kinds of rockets. So first with the solid rockets, they're typically made of aluminium, ammonium and iron, and they're molded into this kind of rubber so that they're made into a solid. And they're kind of like a giant firework. This is the inside of a solid rocket. These are actually the rockets that are used as the solid rocket boosters on the side of the space shuttle. These white things here are solid rockets. This big tank in the middle is a liquid fuel tank. So at the top of the engine you have a small igniter. It's basically a spark plug. There's light, and it sets fire to the inside of here. There's nowhere for the gas to escape at the top. So instead it rushes out to the bottom and gives you a thrust upwards. That's what this huge cloud of smoke here is igniting material on the inside. So they have several advantages and disadvantages. Why would you want to use a solid one? Why would you want to use a liquid one? Well, for a start, they're safer to store. You don't have to carry around containers of compressed oxygen and compressed hydrogen, which explode very easily. So the solid rockets are much easier to store. You can leave them in storage for tens of years and they won't degrade. They're also simpler to build. As I mentioned, it's basically a firecracker or a candle. You just light the end and let it burn. There's no fancy engines, there's no combustion chamber, it's just a giant candle. And this means it's cheaper. Because there's fewer components, it means it's cheaper to build. It means NASA doesn't have to spend quite as much on the shuttle as they used to. But there are certain disadvantages as well. You don't get as much power out of them as you do as a liquid rocket. Because of the way that the chemicals react together, you don't generate as much power when you light it. So that's why the shuttle uses a combination of solid and liquid rockets. You can also carry a lower payload. So what is a payload? A payload basically means how much weight can you carry into space. If you want to carry 5 people and a satellite, that would be your payload. So the solid rockets can carry a lower payload. And probably quite importantly, you can't switch them off very easily. So historic rockets, you just lit the end and you let them burn. There was no way to stop the burn. So if halfway on your launch you kind of started to tip over, you couldn't switch the rockets off, you just had to let them burn. In some more modern rockets, you can now switch them off, but historically it was always very complicated to do so. It added to the price and it added to the complexity. There were more things that could go wrong. And then the other kind is liquid fuel rockets. So this orange tank in the middle contains a mixture of hydrogen and oxygen in separate tanks. This is then, there's no rockets on this tank. The two fuel lines are fed into the back of the shuttle, and then the rockets in the shuttle actually use the fuel. So typically, most of the time, they're combinations of hydrogen and oxygen. If any of you do chemistry, you know if you combine hydrogen and oxygen in the right combinations, you can make H2O, which is water. And this generates a huge amount of energy, much more energy than you would get in solid rockets. So we've got more power because the chemical reaction is much more explosive. Because you've got more power, it means you can carry more things. So if you want to carry lots of heavy satellites, or you want to carry people into space, you might need more power. So this might be a reason why you'd use a liquid rocket. And you can switch these off. The way that these are designed means that you have to have fuel pumps or valves which can let the two chemicals come and combine together. And the design of these means you can switch them off and on easily. And you can also change the amount of thrust that you're generating. So if you find you're going too fast, you can throttle back a bit and slow down. But there's also disadvantages, because you're carrying around these two things which explode, and there's only a very thin membrane between the two. It's quite likely that it will explode, so they're quite difficult to control. They're more complicated because the engine has more pieces in it. It means there's more things to go wrong, so again, more likely to explode. And in fact, many of the Russian rockets that they tried to launch to compete with the US exploded because the design of their fuel tank meant that these two things combined incorrectly and caused huge explosions. And they're also more expensive. If you've got more parts in the engine, it costs you more to build. So how much fuel do they use? It's a pretty colossal fuel tank. So let's do a simple comparison between your average family car and a space shuttle. So here we go, average polluting family car. Say you get about 30 miles per gallon, which is a reasonable average unless you've got a Prius or something. And you do about 12,000 miles a year, that's about 400 gallons of fuel. This produces about 4 tons of CO2 into the atmosphere. And if we multiply that by the whole of the UK, that makes 240 million tons of CO2. That's the amount of gas that the UK produces on average in a year. If we take the average family space shuttle, it uses about 1,000 tons of solid fuel. In these rockets on the side, about 1,000 tons together. But the large tank is just hydrogen and oxygen. So when you combine that, you create water. So there's no emissions. So it's just the solid rocket boosters we need to consider. So for each emission, it produces the equivalent of about 28 tons of CO2, which isn't a huge amount more than 4 tons, which is what your average family car does in a year. If we multiply this by all of the space shuttle launches that happened, which is 135 missions in total, that produces about 4,000 tons of CO2. So when you compare this to what the UK produces in a year, it's really not a huge amount of fuel considering the scientific benefit of doing it. So how much power does it generate? We've got this huge engine. What kind of things can it do? Well, it generates about 12 billion watts. It's quite difficult to imagine what that number means, 12 billion, or so here it is taking off. So at takeoff, when it's generating the maximum power, it generates about 12 billion watts. But it's quite difficult to put a hand on that, so let's make some comparisons. The average light bulb, energy efficient light bulb, uses about 10 watts in your house. You sat here watching this talk, your body is using about 100 watts of power. When you boil a kettle for a cup of tea, it uses about 1,000. If you drove here tonight, when you've got your foot down in your car, you use about 100,000 watts or 100 kilowatts. A typical fighter jet uses between 1 and 5 million watts. So we're still not getting close to the shuttle. One of the heaviest and most powerful commercial airliners is the Boeing 777, which generates about 80 million watts. We're still a few zeros short off the end here. So a nuclear power station you think was pretty powerful. 100 million watts is not to be, it's not to be scoffed at, but it's still not even close to 12 billion. The Hoover Dam, one of the largest dams in the world, generates 2 billion. So now we're getting slightly closer. But this is still a huge hydroelectric power plant, one of America's most powerful power-generating things. It's still a fraction of the shuttle. We have to go to the entire country of Norway in 2000, use the same power as the shuttle. About 12 billion watts exactly is the same power as the shuttle. So as I said, there's lots of different kinds of rockets. Here is the Saturn V rocket. This was the rocket that put man on the moon and for all of the Apollo missions. Here is the space shuttle, the American space shuttle. The next closest big one is the Russian N1 rocket. This never carried any humans, unfortunately. It tried to take off 5 times and blew up all 5 times, but there was nobody on board, so it was just a scientific experiment. Most of these other small rockets are used for carrying GPS satellites or telescopes into space. But this just shows the rich kind of variety of rockets that you can get. They're not all the same. So how far can they go? So they use a few thousand tons of fuel. How far can they go with this fuel? Well, the average passenger airline goes to about 10 kilometers. Some of the weather balloons go to about 40 kilometers, which is kind of getting on for the edge of what we would consider space. The International Space Station, which you might have all heard about, is up to about 300 kilometers. The Hubble Space Telescope, which has produced some amazing pictures of the cosmos, which I'm sure you've all seen in previous talks here. This is at about 600 kilometers. It moves around a little bit, but it's usually about 600. 20,000 kilometers, much further away, are the GPS satellites. So these are so far away so that they don't rotate as quickly compared to the Earth. So when you use your GPS unit, it's typically picking up about 7 or 8 of these satellites, which are overhead at any point in time. And obviously, the more satellites you have, the better you get your accuracy. And then if you want to go to the moon, you have to go 380,000 kilometers, much further than the GPS satellites. So why do we want to put a telescope in space? Why don't we just build a huge telescope on the ground? Well, the problem, as some of you may know from coming to these talks, is that the Earth's atmosphere obscures our view of galaxies and stars. It may be difficult tonight to see any through the layer of cloud. So we put telescopes in space so that we don't have to try and look through this thick layer of atmosphere. So let's look at the Hubble Space Telescope, which was launched in 1990. It was carried on a US space shuttle from Florida. Here it is taking off. If you imagine looking at the Andromeda galaxy from the Earth with some of the best telescopes, this is what you'd see from Earth. And as we go into space, this is what Hubble sees. It gets a much clearer view of the galaxy because there's no gas and dust in the way in our Earth to see it. So going back again, that's what we see from the Earth. And then as we go into space, you can see the brightness increases because we haven't got as much atmosphere to get in the way. So these are some of the images that Hubble has produced. You can buy some of them as postcards outside, I think. So this is a Carina Nebula. It looks quite bright in the picture, but it's actually quite dim. So the exposure time on this picture was a couple of, often up to a day. So you leave it pointing in the same place for a day. If you just looked at this through the naked eye through a telescope, you probably wouldn't be able to see very much. Here's the Orion Nebula, another fantastic picture taken by Hubble. Pinwheel, M101 galaxy. Again, you never get this level of detail from ground-based telescopes, so we have to put things into space to be able to get enough detail. And one of my favourites, which is the Hubble Ultra Deep Field. So they pointed it at a patch of space that they thought was empty. There was nothing there that they could see, and they just left it there for several days. And this was the picture that they got. Thousands and thousands of previously undiscovered galaxies in this apparently empty patch of space. So this is one of the great reasons why we need these rockets to send these huge telescopes into space. So another one of the most famous things that are in space is the International Space Station. This is a collaboration between tens of countries all around the world, and they've all built different bits of the space station, launched them, and then they then joined them together. So the original part was launched in 1998 on the US Space Shuttle, and since that time over 15 different parts of it have been launched, but not all on the Space Shuttle. So here's a Russian Proton rocket. This was used to ferry over half of the parts of the ISS. Doesn't generate as much power as the shuttle, but the bits that it carried weren't as heavy. And the other famous one is the Russian Soyuz rocket. So this generates about the same power as the Proton rocket, but not as much as the shuttle. And again, they're both used to carry different parts of the ISS to space. Now, because the space shuttle has recently been retired, the only way to get to the ISS now is using these Russian rockets. So if we want to bring our astronauts home and put new experiments in space, we have to now rely on the Russians. So this is a view of the ISS. This is one of the most fantastic videos I think I've seen from the International Space Station. But it highlights an important point. So we've used a rocket to put this thing in space, but we can't just leave it there. The ISS has rockets on it which help to keep it in the same orbit. So you can see this green layer, which is forms part of the aurora borealis. This is an indication of roughly where the atmosphere layer is on the Earth. So as the ISS rotates around the world, it hits into the atmosphere, and this causes a friction. This slows the space station down. Now, if it slows down too much, it could drop down to a lower orbit, start heating up, and this could be dangerous for the people that live on it and for the experiment. So you've got to keep it at the same orbit at about 300 kilometers. So about every 2 months, there are 2 rockets on the International Space Station. They fire for about a day to push the space station back up into its highest orbit. If they didn't do this every month, then it would eventually descend into the atmosphere and would risk burning up. If you want to look at this video afterwards, if you do a Google search for ISS low light camera, there's a brilliant HD video on YouTube of this. So what about other experiments that are happening here at the IOA? So I work on something called the Planck satellite, as do about 25 people in this department. And this was launched on a rocket from South America in a place called French Guiana. It's named after the famous physicist Max Planck, who is unfortunately no longer around to see it, but I'm sure he'd be very proud. So here it is launching. This is called the Kourou spaceport, which is in South America. It was launched in 2009 on what's called an Ariane 5 rocket, which is this thing here. So here are the 2 clamps being taken away. The 2 main solid rocket boosters fire in a second. Here you can see the stream of water to deflect some of the energy of the blast. My supervisor was probably sat somewhere here. Unfortunately, I didn't get a holiday to South America, but apparently I wasn't valuable enough then. So it's 15 meters tall. It weighs 800 tons when it's full of fuel. And it can carry a 10-ton payload. So you can see the difference between the weight of the rocket, which is 800 tons, and the maximum weight of the thing it can carry, which is only 10 tons. So you need 80 times as much weight to carry something into space. So it consists of 2 solid rockets and 1 main liquid rocket in the center. So it's got a very similar design to the way that the space shuttle is laid out. So here's the inside of the space shuttle. Here's the main stage. This is a hydrogen. So this is oxygen, and this is hydrogen. Here are the 2 main solid rocket boosters that you saw firing a second ago. And here are the 2 scientific experiments in the top. Notice how small they are compared to the overall size of the rocket. So where are the 2 things located inside the rocket? The first one is called Planck. It's located up here. And on top of it is another space telescope called Herschel. So Herschel is a different kind of telescope that, again, about 10 or 15 people in this department work on. And Planck is actually mentioned on your handout tonight. I discovered a few minutes ago. So if you want some more information, just have a read of your handout. So where did the rocket take Planck and Herschel to? Well, Planck and Herschel now sit about 1 million miles away, or 1.5 million kilometers away from Earth. Here's the Earth-Sun distance, which is 150 million kilometers. The rocket left Earth, travelled to the far side of the Moon, and is now sat in a point called the L2 point. The L2 point is a fancy name for a point you can put something and it will stay there. You don't have to give it any extra fuel to keep it in its orbit. As this system rotates around, the 2 satellites will stay in almost exactly the same place. You don't have to give them extra fuel to keep them in their orbit. So this is what the Planck satellite looks like in space. It does have 2 very small rockets attached to it, one here and one's on the other side. But they're not used to keep it in orbit. They're used to give it a gentle spin when it gets to its final point. So Planck isn't like a usual telescope. It doesn't point at something and take a picture. It scans the entire sky. So it rotates at about 1 revolution per minute and scans the entire sky, picking up information about our own galaxy. So it doesn't really have this blue beam. That's just to show where it's looking as it spins around. So this picture you can see being built up now is a picture of our own galaxy. This red line in the middle is all the gas and dust that's in the Milky Way, which is giving a strong signal. And this signal at the top and the bottom is much less from the galaxy and more from what's called the echo of creation. So it's thought that when the universe was created, the shock waves that were sent through space generated this radiation. And this is a pattern that we can see on the microwave sky. So that means, just like Hubble uses optical light to get visual pictures, the Planck satellite uses microwaves to get pictures of the galaxy. And you can see it there being overlaid onto optical pictures of the galaxy. So this was, it was launched in 2009, but it's had several data releases since then. It's been working for about 3 years now. But after the first year, it completed 2 full surveys of the sky, and this was the picture that it generated. This was one of the highest detailed pictures of our galaxy that has ever been taken. So the purple here is all of the gas and dust. The pink is the hot electrons in the middle of our galaxy, and the pink stuff on the top and the bottom is this echo of creation, or the cosmic background radiation. So Herschel was a slightly different telescope. It's more one that you point at something and you take a picture of it. It's very sensitive to dust emission, so it takes pictures of dust. But dust might sound a bit boring, but I think these pictures are pretty cool. It has various frequency channels, so it can build up an interesting picture of what the dust looks like in different frequencies. So each of the different colours here are representative of the different channels of frequency that are on the satellite. So, what's the future of rockets then? Well, we've talked about how they're used in astronomy, but what happens next? Well, there are several ideas for the future of rockets. Some of you might have heard there was a mission that wanted to go to Mars. Unfortunately, due to the bankers in London, we can't go to Mars anymore because there's not enough money, but maybe one day we will. And this is the rocket that's been designed and proposed as the rocket that should take man to Mars. It's almost twice the size of the space shuttle, 1.5 times the size of the Saturn V rocket, which is the largest ever rocket that's been built in history. It carries almost twice as much fuel and is designed to carry up to 12 people and 2 scientific satellites. So the humans would live in this tiny bit at the top here. Here's your main liquid rocket, and here's the 2 solid rockets at the side. Other kind of rockets, so let's talk of something called an ion rocket. So it doesn't work in the same way as a liquid or a solid rocket that I've talked about. So ion rockets work by accelerating charged particles in what's called an electric field. So kind of like the way that old TVs work, if any of you still got some of the old CRT monitors, they work by accelerating particles through an electric field. And these ion rockets work in the same way. So you have some block of fuel here that you slowly heat. Bits of the block of fuel break off and are then accelerated. And just like the way other rockets work, they're shot out the back at high speed. This then pushes the rocket forward in this direction. So the advantage of these is they run for years and years because you only get a very tiny thrust, so you could never use them to take off from Earth. But once they're in space, they'll last for years. And even though the acceleration is very small, over the space of a year, they can accelerate satellites to hundreds of thousands of kilometers per hour. So that's one of the proposed methods of sending scientific instruments to faraway planets in very short spaces of time. The other option is laser rockets. So this kind of technology is mainly for things that are still in the Earth's, still close to the Earth, but not traveling to Mars or another planet. So the way these work is pretty cool, actually. You have a huge laser on the floor, on the ground in your space station in Florida, and you shine your laser up to the rocket. Now the rocket has special panels on the bottom that accept this laser light, turn it into heat, and then use that as energy to power the rockets. So the rocket doesn't carry any of its own fuel. We're beaming the energy to the rocket with a laser. So technology like this is already in existence. There are already designs for rockets that use it, and satellites. It's proposed as a method to power GPS satellites that need more power than they could get from solar panels. So all of these technologies are currently in development. There are no rockets that use them at the moment, but within the next 10 years, some of these technologies might be used to put rockets into space. So that's about done for the history and the design of rockets, but I thought I'd put a nice slide on here about how to make your own rocket when you go home. So I've put a film canister on here. I'm not sure whether these are still in circulation anymore. They used to be, you get them with analog cameras and you have a little bit of film in, but with digital cameras, I'm not sure you can get them anymore. But if you do, if your parents have any film canisters, or you can even use Tupperware containers, small Tupperware plastic containers. So what you'll need is, your film canister forms the basis of your rocket. You need a bit of paper to make the rocket itself. So here's the bit of paper. You wrap the bit of paper around the film canister, put some sellotapes in, give it some speed stripes, a nice nose cone that you can sellotape onto the top, and then you need your fuel. Unfortunately, it's a bit dangerous to be mixing oxygen and hydrogen in your own bedroom, so instead of that, you can use 2 different kinds of fuel depending on how much power you want your rocket to have. One of them is called bicarbonate of soda mixed with vinegar. So ask your parents if they have any of this in the kitchen. They might do if they bake. Or you can use water mixed with a fizzy aspirin or a fizzy headache tablet. So when you put your rocket together, turn it upside down, pour your fuel in. This one I've put in red because it generates much more power than this one. So you turn your rocket upside down, you tip your fuel in, quickly put the lid on and set it down. And give it about 5 to 10 seconds, and the lid will blow off due to the pressure created by the fuel and send your rocket skyward. With this fuel, you can get to about ½ a meter high. If you put the right mixture of this fuel in, you can get to about 2 meters high if you're lucky. But make sure you use eye protection or stand well back when this takes off. So that's about it for the summary. I'll just summarize quickly. So the next time you use your GPS unit in your car to get home, if you've got satellite phones, if you've got Sky Television, if you've ever used Google Earth, which is very popular nowadays, the picture version, not the map, or indeed weather reports, all of these technologies have in some way used rockets, and especially GPS, where there are thousands and thousands of GPS satellites orbiting the Earth at the moment. So the next time you use any of these, think of all the rockets used and the amazing technology used to drive your digital devices. I'll take any questions now. Thank you very much.
I was wondering which takes more rocket fuel to get to the Mercury mission or to the outer solar system?
So the question was, which takes more fuel, the Mercury mission or to get to the outer solar system? Well, it depends which kind of fuel you use. So the plans to get to the outer solar system, it's been proposed that you could use these ion rockets because they'll last for longer and you can control the thrust for a longer period of time. But again, if you want to send a probe to Mercury, it's not as far as to the edge of the solar system, so you can probably get away with using conventional rockets. But with the Mercury mission, when you get there, you probably want to move your satellite around a little bit. So for that, you won't be able to use ion engines, you'll have to use conventional rockets. So when I was talking about the Planck satellite, it has these tiny little rockets on the side that just help it spin around. They don't generate much power, but when you're in the vacuum of space, you don't need much power, you just need to give it a little squirt and it will spin it around. So if you use those kind of rockets for the Mercury mission, you can actually turn your rocket around when you get there. Whereas if you want to go to the edge of the solar system, you're more interested in just passing planets as you get to the edge, so you could probably get away with using an ion engine for that.
Is space junk becoming a problem?
Is space junk becoming a problem? Yes, definitely. So there was a report last week by NASA about close encounters that the International Space Station had had. And there was a huge detailed report about which parts of it were most vulnerable to impact. Now you might not think it's a very big problem, but if you have a fleck of paint travelling, so a bit of paint that's broken off of a satellite or a GPS unit, that fleck of paint is likely to be travelling at something like 50,000 miles an hour. So when it hits your satellite, it will cause a huge explosion. It's only a tiny fleck of paint, but because of the energy it has because of travelling so fast, it can rip a huge hole in your spaceship. So there used to be a space station called the Mir space station, which was a Russian space station. And on 5 separate occasions, all of the crew had to evacuate into the evacuation module because the Russian space agency had detected that there was a bit of space junk on its way to Mir. And they had about 3 hours from when it was detected to when they had to get all of their equipment out into the evacuation module. Luckily, it didn't ever explode the capsule, but there were a few close calls. And when you bring back astronaut suits, when astronauts have done spacewalks, if you look at these under a microscope, they look like a cheese. There's hundreds and thousands of tiny little holes in the spacesuit, which is where tiny dust particles have caused holes in these. And over time, if you do several spacewalks, the spacesuit starts to depressurize because of all these tiny holes. Each hole only makes a tiny difference, but when there's thousands of them, it can be a very big problem. So yes, it's a very big problem, and especially if you spent a few million putting a GPS satellite up there and another bit of space junk just smashes into it. I'll be quite annoyed. So yes, it's a very big problem, but there are plans underway to send space hoovers up, which are thought to be, it's just designs at the moment, but it's basically a rocket that goes and picks up all of these things and pushes them into lower orbit, so they eventually crash and burn up into the sea. And I think it's only going to get worse as we put more GPS satellites into space and more low Earth satellites. I think there's something like 50,000 satellites of some kind or another orbiting in the Earth, and they're all in very similar orbits. And there has been collisions, and it's only going to get worse, so I think something has to be done, but something is being done. Yeah? So how do you make sure the rocket doesn't blow up? So this is obviously a very big problem. It's quite a catastrophic thing to go wrong if your rocket blows up. So the way that these designs are taken into account, so as rockets were developed, the first rockets used to blow up all the time. But each time they did it, they found something that was wrong with it, and they managed to correct it for the next one. And then the next launch, it would last a bit longer before it blew up. And then they found what was wrong that time. So over the course of 20 or 30 years of designing thousands of rockets, scientists managed to work out exactly what was going wrong each time and try and correct that. Just tiny adjustments to the way that the engines work, changing the material slightly that you use, all help to keep the rockets intact and not explode. Yeah? So why did the US stop sending space shuttles to the moon? Well, I think it's very sad that they did. Unfortunately, there was, in their mind, I think there was very little more to be gained by putting men into space and onto the moon and even to Mars. It's much easier and cheaper to send a robot to Mars, as maybe some of you know about these Mars rovers that have recently landed and brought back amazing pictures. It's much cheaper and easier to send a robot to do the job. So that's why they did. I think it's very sad, and I hope that Richard Branson's Virgin Galactic, or whatever it's called, is going to ignite a new generation of people who want to go into space.
Are they still doing space? Are they still sending people to space?
Yeah, so there are still the International Space Station is still the longest inhabited thing in space. I think there's about 8 people up there at the moment, and every year or two they send up a different crew of people and bring the original crew back. So yes, they're still in space at the International Space Station, but not going to other planets yet. Any other questions? Okay, well, thank you very much. I think we're breaking for coffee now, but I hope you all enjoyed the talk, and shame we're not going to get to observe, but thank you very much for coming.